No,
Okay, listen, please. No one talk. Make sure your phones are put away. If you use the calculator for a couple of days, listen, hey, we use the calculator for a couple of days to make sure that when you had a calculator, to give me the chance to introduce a few calculator functions. We actually won't use the calculator now probably for a couple of months. I will remind you when you need to bring it again. So you don't want to pack it around, you don't have to. When I was a student working a packet like this, I think I mentioned I found it very annoying if I had to look at this picture or look at my calculator and then just keep going back and forth. So to prevent that, to get you to focus on the big idea, not the little details, what you should do is tear off the back sheet. The graph that is on page 9 is what you will use to answer all of the questions. There you go. Good sound effect. The graph on page 9 is what you will use.
That was a terrible.
Yeah, it was. You didn't make any sound effects.
Look out. Hey. Look out. So page 9 is the graph for the first half. Page 10 is the graph for the second half. So, here we go.
Okay.
Question 1 says, okay, look, the entire packet, listen close, okay, the entire packet is trying to get you to see how two things correspond. So when you read the question, don't read it in sequence, kind of jump around a little bit, looking to see what they're searching for as far as the correspondence. So for example, right here, it says use position to determine when the particle's position is decreasing. So we've already done that. We've discussed that on previous days. If I'm just looking at position and I want to see, let's see, we're starting at time equals 0. So beginning at time equals 0, if I follow the numbers, I find that my position is becoming increasingly negative all the way to this time. So that would be when I would be most left, and then the position becomes more and more, I should say less and less negative, meaning I'm now moving to the right. So I know the position is decreasing, particle's moving left, starting at time 0 and going all the way to time 4.848. Questions on that about anything? We've done that before, it's not new. So. Next one. Okay, now, here's the correspondence you're supposed to be identifying. So we know that for all of this time I've shown in green, the particle is moving left, meaning the position is decreasing. Well, when the position is decreasing, you can be assured that the velocity will have to have negative values, because the velocity tells you how the position changes. So if the position is going down, the only way for the position to go down is if the velocity is negative, because the velocity tells you how the position will change. So therefore, the velocity graph must be negative for that same time period. And of course, we already answered this one. Therefore, the particle is moving to the left for that same time period. On the test you will take in a couple of weeks, 80% of your grade, remember, no pressure. They're not going to give you all 3 graphs. They will give you one of them, and then they'll ask you questions. They'll ask you to figure out, okay, if I'm just looking at velocity, they'll ask you questions about position. That's the whole idea. On the homework, I'm giving you all 3 so that you have a chance to see how they correspond. But on the test, they're going to test your memory to see how well you remember how they correspond. That's the beauty of Danika's chart. It's a quick, concise way to remember how the 3 graphs, how the 3 sets of data correspond. So, questions about anything? Cool. Number 2. A couple of definitions here. The first definition we'll talk about is over here on the right. It says any function. These definitions are on the reference sheet that I just handed you. And what I found that works best is you put it on cardstock, you put it in a sheet protector, and then at the end of Unit 1, you take out all of your homework packets and you just put them somewhere at home in case you need them, but you don't have to carry them with you all the time. You carry this with you. This is usually sufficient when we get to Unit 3 to remind you of all the things you learned in Unit 1. Like you won't have to go back to the homework. The purpose of the homework was to reinforce these ideas, but this is probably all you'll need for like Unit 3 to carry with you from Unit 1. Look at the card. So we look up. Take note of the side I'm showing you. That's where all the information that's key is located. The other side is more of like an extra. Has a bunch of extra examples that some students use, others never look at them. Just depends. Seen it go both ways. Like I never thought to make this because this made sense to me. But some students wanted some extra information, so this was created. The definition we're talking about right now is on the reference sheet. It says any function, for example, position. Any function, could be position, could be velocity, could be whatever, has a relative or local maximum. The definition is simply the opposite for relative minimum, so I didn't write it down, but it's the same idea. When that same function, so the purple function being position, has a relative or local max, when that same function changes increase to decrease. And there's a big or, so I'm going to change color. Or when the function's derivative. Okay, the function's derivative of position would be velocity. Changes positive to negative. So what that definition is saying is, if you're looking at position, and you notice the position change from increase to decrease, that would be a relative max on the position graph. But on the test, you probably won't be asked that kind of a question. What you'll be asked to do is look at the derivative of position, which is velocity, and identify from the derivative when the position has a relative max. So when velocity does this kind of a change, from positive y coordinates to negative y coordinates, that's indicating that this other graph that you might not be able to see has a relative max. It's not a relative max on velocity. It's simply the velocity is indicating that the position has a relative max. That was a lot of words. Questions coming to mind from anyone? Please ask.
So that was only positive to negative. Is there a relative or local minimum?
2 points, 2 points. Yeah, the definition is exactly the same, just the opposite. Oh yeah, you're good. I don't remember what I put on here. Yeah, what I did, Aspen, is I only listed the local max definition because I assumed that everyone would do exactly what you did. Just think about it, okay, the relative min is just the opposite of that. Other questions coming to mind? Okay, cool. So using that definition, raise your hand if you could tell me where does, it's kind of a trick question, where does the position graph have a relative maximum? Raise your hand if you know. It's a bit of a trick question. So using this definition that we just talked about, where does the position graph have a relative maximum? So keep your hands up for a second. I'm going to just say it again. It says any function. So if you're looking for where the position graph has a relative max, and you can look at position, then you would say, I'm looking for where that position graph changes from going up to going down. And if I can find that location on position, then I will know that the position graph has a relative max? So who can answer the question? Where does the position graph have a relative max? HT?
I think there isn't one.
So HT claims that there is no relative max on position. How many would agree with HT? 0.2 for HT. Yeah, that's why I said it's kind of a trick question. There really isn't a relative max because the graph of position, it's hard to see right here, but based on as best we can tell, the position graph never changes from increase to decrease. Question? Please, Jason.
So it's only when it's changing from increasing to decreasing.
So decreasing to increasing would be a relative minimum.
Oh.
And then the other word they'll use is extrema. Extrema means either. 2 points for Gabe. Here's another trick question. Raise your hand, please, if you can tell me. Does the velocity graph ever change from positive y coordinates to negative y coordinates? Hands up. Does the velocity graph ever change from having positive y coordinates to having negative y coordinates? Let's go, Jane.
No, it goes from negative to positive.
So the velocity graph, and the Danika's chart is showing us that correspondence. We never found anywhere where the position changed from increase to decrease. Therefore, it is impossible for the velocity to ever change from positive to negative. How many knew? 0.2 for Jane. Raise your hand if you can find the relative minimum on position. Like at what time does position show a relative minimum? What is the time when position shows a relative minimum? Let's go, Ian.
4.8%.
So right here, we see the position graph changing from decrease to increase. How many saw it? 0.2 for Ian. That is exactly the same time when the velocity graph changes from having negative y coordinates to having positive y coordinates. That's what Danika's chart tells you. Questions about anything? So one more time, raise your hand please if you can answer. Actually do this, I want you to vote. So this means position. This means velocity. This is acceleration. This would be position and velocity. This would be velocity and acceleration. A vote of 0 means you really don't know. It's better not to guess. Guessing in this class usually makes it worse. So if you don't know, you just don't know. So the question is this. I'm going to make a statement. You answer it by voting. What graph or graphs have a relative min at time 4.848? So which graph or graphs have a relative minimum at time 4.848? Show me your vote. Okay.
That's the
You're
one.
doing just fine. Okay, everybody gets a point for voting. If you voted this, you get an extra point. A few people got mixed up. The answer is not 4. We use velocity to identify where the position has a relative minimum, but the velocity does not have a relative minimum at that point. The velocity is not changing decrease to increase at that time. Question. Risha, if you know where the velocity has a relative max, hands up. Where does the velocity have a relative maximum? Where does the velocity have a relative maximum? Let's go, Cecily.
At 0.202 seconds.
How many agree? 0.2 for Cecily. That is only the relative max on the velocity. Now, if you look at the acceleration, you'll notice that the acceleration is changing from positive y coordinates to negative y coordinates. That's telling you that that velocity graph has a relative max at that spot. But it is not the relative max of acceleration, just velocity. Question? Please.
Should 4 and less than be x of t, not x of x?
Oh, thank you. 2 points. Okay, cool. Next definition. It says a function has a critical point. So any function has a critical point when the tangent slope of that function is either 0 or undefined. So if I'm looking specifically at the function, like I'm looking at position, I notice that right here, the tangent slope of position would be 0. That means the position graph has a critical point at that time. The other way to determine the critical point on position, the way you'll more likely do it on a test, is the second part of the definition, which says, or when that function's derivative, the derivative of position is velocity, has a y value of 0. So sure enough, right here, when the velocity graph has a y coordinate of 0, that means the position graph has a critical point at that same spot. Questions? Awesome.
Say that one more time.
Yes, one more time. It's again, it's all about how does this tell about this. So if I'm looking at just the blue, which this is not going to be tested very often, but if I'm looking at the blue and I want to find the critical points on the blue, on position, I look for places on position where the tangent slope is 0. So I find that here. You good there? That means time 4.848 is a critical point of position because of that. On the test, what will more likely happen is you won't see the blue. You'll only see the derivative of position, which is velocity. And you'll have to say, okay, looking at the velocity graph, can I figure out when the position has a critical point? And you can, because the position will have a critical point when the position's derivative, which is velocity, has a y value of 0.
Oh, okay.
Point. Please.
What is a critical point?
So it's just a name that they're giving to that type of a feature. That's really it. So you think of it two ways, Jackson. Hey, position has a critical point anywhere where I see the position graph having a tangent slope of 0. So that's at this time. But the other way to determine that is to say, well, the velocity is the derivative of the position, and derivative means tangent slope of the position. So right there, that y coordinate being 0 tells me that the blue graph has a critical point at that time. It's not the orange graph. 2 points, please.
Would there be like a derivative of acceleration at all that we would ever need to know?
We don't name it for this class. In physics, they give it a name. They call it the jerk. Okay? But yeah, you can find the derivative of acceleration, and then the same thing, the same rules apply.
Okay.
2 points.
Just be like a line going on like that, crossing through the.
For this example where all 4 graphs are polynomials, you are correct. The derivative of acceleration will be a line like so-ish. The derivative of that's going to be like that. Yep. And then the derivative of that will be 0, and then everything after that is just 0 forevermore. Yeah, that's true of polynomials. Not true of all the kind of functions we'll study. So don't lock that into your memory like that's a pattern that will always exist. But it does exist if they're polynomials. 2 more, Tara.
So how do you figure out that the tangent slope is 0? Like, how do you figure out the tangent?
No worries. 2 points. The simplest, well, a way to think of tangent slope is this. Slope means rate of change, like how fast are the points changing from one point to the next. For example, you learned some time ago that if you have a point here and a point here, and you go calculate, okay, how much is the y value changing? You compare it to how much the x value is changing, rise over run, that's slope. Tangent slope is the exact same idea, you just have to imagine that you get to zoom way in. So you get to zoom in so close that these dots are like very close together. But you're still finding how fast they're changing. Visually, it's easier to do this. Right here is a curve. But if you focus on one point, like right here, and you zoom in very, very close, Tara, would you see a curve or would you see a straight line?
Curve.
So if you get closer and closer and closer, eventually the curve appears straight, just because you're so close to it. Agreed?
Agreed.
Okay? That means you could observe the slope when you zoom way in. That's what we refer to as the tangent slope. It's like, what slope would we observe? Like, how fast is the velocity changing at that instant? That's what we mean by tangent slope. So right here, the tangent slope is whatever that slope is. So it's some positive number. Right here, the slope is more or less positive. So this slope compared to this one, which one is more positive, the first or the second?
The first.
The first is more positive, it's steeper. So this slope is greater than that slope. You keep following the curve, that slope is even less positive. When we get to the top of the curve, we get a horizontal slope, that's a slope of 0. So going back to 2 points for Tara, Jackson's question, if you're looking at velocity, that spot where you see the velocity having a tangent slope of 0, let's vote. So right there where you see velocity having a tangent slope of 0, which of these has a critical point at that time? So right there. So that spot where you see the tangent slope having the velocity having a tangent slope of 0, vote. Which of those has a critical point? Here's the definition. So when that thing curves over, which of these has a critical point at that spot? And 2 points for everyone for voting. We're kind of all over the map. Right at that moment, the velocity absolutely has a tangent slope of 0. So the velocity has a critical point at this time. Questions about that?
It kind of looks like a position.
2 points. As best we can see, it looks like the position goes flat as well. There's no way for you to know otherwise. So that's a totally valid answer. If you zoom in really close, you can barely see that the velocity the velocity slope gets to 0, but the velocity itself never gets to 0. So that means that the position graph never really goes flat, because the velocity is always showing you the slope. That's not what I wanted. The velocity is always showing you the slope or rate of change of the position. So again, 2 for Aspen, but the position actually doesn't flatten out there. If it did, the position would also have a critical point.
Okay, but would we get marked wrong on the test for saying that?
You would not. If all you could see is this, you would not be marked wrong, because there's no way they can expect you to be able to visually identify that. They'll give you some more information so you know. They might do this. Look. Okay, here's a really good test question. I've been telling you since the first of the year that the test questions will feel different than the homework, but they will probe your understanding. So everybody see if you can answer this one. I said to Aspen, if they give you this picture on a test, they cannot expect you to identify, what's really going on here, because you can't see it well enough. So what they do is they give you an extra clue. They show you all this, and they also say on the test, for the graph goes from -2 to 7. So for this span of time, the velocity values, actually let's don't do it that way. They'll say from like -2 to, what's this number here, 4.848. They'll tell you that for that span of time, the velocity is always negative. Once they tell you that, you now know that the position cannot have a critical point anywhere in that span. Because the definition says if the position is going to have a critical point, the derivative of the position has to have a y value of 0. But if the velocity is always less than 0 in that span, the position can't have a critical point in that span. Jake?
How could it not be 0 because it's less than or equal to 4.8? Is that just make it improvement?
Oh, 2 points. You're just mixing up time versus velocity. So it's saying, when you look at the graph, you're looking at two things at the same time. Time is the x values, velocity is the y coordinates. So every one of these orange dots has a time and a velocity associated with it. Looking at the dots that begin at x equal time equal -2 all the way to time equal 4.848, none of those dots will have a y coordinate that is positive. That helped. 2 more. Other questions?
So you're saying that the velocity graph doesn't have to actually reach 0 at that spot?
Correct, because you can't see whether or not it does because it's too compressed, so they tell you it doesn't.
How does that tell you that it doesn't?
So this is referring to,
It's less than 0 from like negative. Oh, I see. Yeah.
you with me?
Yeah. So at that spot, it's still within the range of it. It's less than 0.
Still has to be less than 0.
Okay.
That's the kind of thing. 1 second, kid. 2 more for Aspen. Everybody look. This is what you're practicing for the test. Is this idea that you get some information that you may never have seen presented this way. You have to think through it and say, okay, what is that telling me? This is telling me in this span, none of these orange dots will be ever anything but negative. Which means I cannot have any critical points on position in that span. Because for a critical point of position to occur, the velocity would have to equal 0 or undefined. Okay, good. 2 more. Who else? Please.
What did it equal 0 when it was 4.8?
Thank you. That would be a mistake on my part. So. Does this make better sense, Lily? Nicely done. Nicely done. Yeah, when we get to 8 point, when we get to this time, it does equal 0. So that would be inconsistent. Perfect. Anybody else? Solid. Okay. Let's go to the actual written question here. It should be fairly straightforward now. The position graph is increasing. So you're focusing on position increasing. Again, I don't just fill in the blanks. I look for the correspondence because that's what the packet's all about. So position is increasing. Position is increasing from some time to time 7. Okay, right here. So from this point onward, the position graph is going up. Therefore, the velocity graph, change color, must be positive. For that same time span. And notice that starting at time 4.848, when the position graph starts to go up, every y coordinate on velocity would have to be a positive number. Because the velocity is always telling you how the position is going to change. If the velocity is positive, that means the position must be going up. Questions? Cool, keep going. Part B, therefore the position function, back to green. Okay, they're focused on this time right here. And we're noticing that what the position did is, as we discussed, the position went decrease, and then the position went increase. So the position has a relative, or local min, at that time. Questions?
Could you also say therefore that the tangent slope equals 0 at that point, or no?
I'm going to pay a ticket for that one. The graph so listen to what Tara said. The graph we're discussing right now, the position graph has a local min here, and at that spot, the position graph also has a critical point because the tangent slope right there is also 0. We will encounter problems in the future that don't have that shape. They'll do this instead. They'll, hold on. They'll show a graph that does something like this. Okay? We'll call this the position graph. Okay, this means true, this means false. Show me your vote. This graph of position has a relative minimum right there. True or false? Show me. That graph of position has a relative minimum at that spot. True or false? Show me your vote. So the correct answer is true. Point if you voted. This is position. The definition on your salmon-colored reference sheet says that if the position itself changes from decrease to increase, then the position has a relative min at that spot. Please.
What if the graph kept going down further later? Would they just both be considered relative mins?
So, something like this.
Exactly.
So now this graph of position has two relative minima. Or mins, either way. Does that answer your question?
Wait,
Yeah.
minima is a word?
Say again.
Minima is a
Minima
word?
is the plural of minimum.
Would you have to
What?
say that on the test?
No, if you say minimums, they're okay.
Okay, I was like-
They don't care about that. In fact, I have to be honest, I struggle to say minima. I don't know. It's the right word, but I just always say minimums. So, does that answer your question, Preston?
Yeah.
2 points, 2 for Nadia. Anybody else? I owe Tara a ticket. All I do is want you to talk. I pay whenever you talk, and it's in a productive fashion. I accept clever comments, anything that's a part of the discussion. Please, Preston.
Is there a difference between like relative and local minimums?
Also, good question. 2 more. No, for whatever reason, they will use both words. They won't use they won't use both words in one problem, but you'll read one problem and it'll use the word relative. And then 5 pages later, suddenly they'll use the word local.
And it's the same.
Same thing. Same thing.
When we answer it, did you want to use both words or is it just one?
One is sufficient. Hey, 2 more for Aspen. Look, the reason on the worksheet I'm having you write both is just to introduce you to the idea that they can use either. You don't have to use both. Not yet.
Do we, like, say that was on the test, would we use the one that they stated or would they drop us points if?
Either one.
Okay.
Yeah, they're okay with that. Tara?
So Natalie just brought up a good point. On that one, where it's like a bird, wouldn't that one still have a tangent slope or no? Because it's just
It would,
it's
yeah.
bouncing.
A tangent slope of 0.
So everybody look, this is very good. No, 2 for Tara, 2 for Natalie, even though she spun for Natalie. 2 for Kylie, sorry, Kylie.
Kaylee.
Dang! Kaylee, bitch. Is it Kaylee?
Yeah, Kaylee.
K-Y-L-W. Sweetie, take it for the wrong name.
Yay!
Okay, look. Hey, the question is, look at me, come on. The question is dead on target, they're gonna ask it. Go back to Tara's question about what do we mean by tangent slope. And think of that idea of zooming in.
Yeah.
When you zoom in on a curve, like here, hey, come on. When you zoom in on a curve and you get closer and closer and closer, just go like this if this makes sense. The curve appears flatter and flatter. Okay, eventually you get so close you can't tell that it's a curve. It's like the surface of the Earth.
Yeah, I was gonna say
It's
that.
right. HT, the Earth is curved.
Is around.
Okay, despite some people's claims, the Earth is curved. Okay,
Over here.
but you don't look at the ground and think of the ground as curved. You think of it as flat. Okay, but go to this one. Look, hey.
Flat earthers.
No matter how close you zoom in, it will never stop looking like a corner. Like it will always have a sharp point. If you,
Not on
Because
that
only
drawing.
one point
Gradual,
is-
whereas that's just
only
like.
one-
Yeah.
But if you zoom in
They're
close enough
curving
to anything.
toward each other.
well, you're saying if you zoomed in so close, all you can see is the one point anymore.
And it
Here-
would be straight.
It would just be a point. Hey, try this one. Look, 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 look.
That's true.
You learned, look, everybody, come on, look. Focus. Come back. You learned to find slope, you go from point to point, right? Like you say, I'm going to find the slope from here to here. So I find the change in y divided by the change in x. On a curve, when you do that, what happens is you've got the point in the middle, you're finding the slope to the left, you're finding the slope to the right. And the closer and closer you get, these dots get closer and closer. So the two slopes become almost identical. With a corner, that never happens. The slope on one side will always be distinctly different than the slope on the other. We'll get into it later more, but mathematically, because those two slopes never become infinitesimally close, we can't find the slope at a corner. So this slope is undefined. But that's part of the definition on your salmon sheet. It says, if the position graph has a slope that is undefined, that's a critical point of position. So
There's a corner right here.
that's what I call a corner. No question. We go back to here. Anything else? Oh, so here we go. So the position graph has a critical point. At that time, now careful here, the position has a critical point at that time. One of the reasons we know that is because the velocity at that time has a value of 0. Questions? Cool, next one, number 3. Everybody do number 3. I'm just going to walk around the room. Go. Stop me if you want to talk about it.
Therefore, the acceleration is positive. Oh, you're right. You're right. I was thinking we walked and then the two moving forward.
Yeah, switches.
Because isn't it -0.2?
But from 0 to positive and
Yeah.
But the acceleration.
No, she's
Which
right.
would make any difference in the acceleration.
Except not at 0. It's not your choice. No, because the acceleration is still negative, like it's accelerating negatively. And except here, and it's just accelerating positive.
Yeah, that's
How about that?
You're taking it a bit far out.
Which one?
I think I
It says, so if you look at the graph, it says the velocity graph is equal. You have to look really close. Basically, you're looking at an acceleration. So an acceleration is positive, velocity is increasing.
Really, really good.
So the velocity is increasing until this number, and then it says it's decreasing until that number.
That's fine. It's increasing from 0 to 0.20. That is so.
Yeah, no, that makes sense. That makes complete sense.
The same 3 lines over and over and over again.
So that means from here to
Try this God takes
And
me
it's
to
starting to
the top
slow
one
down.
for 15 minutes. That's awesome. Fire song.
It's so.
Have you heard the extended version of STP?
Okay, hey, Danika, you can always check your answers in the back. I'm not concerned whether you have the right answer or not. I'm concerned if you have anything that's bothering you about that item.
I do.
Okay.
Yeah, we know you do.
Camera's bothering me.
The further it gets from 0, the faster the velocity is.
Don't say the word "it." The further what gets from.
Acceleration.
So say it one more time.
I'm just.
The farther away from 0 the acceleration graph gets, the more change to the velocity graph occurs.
That is correct. The acceleration tells you how to for HT. The acceleration tells you how fast the velocity is changing.
Yeah.
So he is correct. Like down here, it's all about slope. Look, if you look at the slopes of the velocity, okay, raise your hand. What's the tangent slope of the velocity right at this time? Hands up. Hands up. What's the tangent slope of the velocity right at that moment, Claire? How many knew? 0.2 for Claire. Look, at that moment, because listen, you have to concentrate on the words. This class is all about precision. Like, look at me. I had a student in this morning. He made a huge mistake. Like he's trying to succeed in calculus how he succeeded in secondary 3. It's not going to work. He's like, well, the word said velocity, so I just did some velocity stuff. I'm like, no, you got to understand what it's talking about. So listen carefully to the words. At time point 202, the tangent slope of the velocity is 0. That means at that moment, the velocity is not changing because slope is rate of change. So at that moment, the velocity is not changing. So the acceleration, which is the rate of change of velocity, has to be 0. That's why right there, the value of the acceleration is precisely 0. Now as I follow the curve, say it out loud as a class. Right here is the tangent slope of velocity, positive or negative? Say it. Negative. That means the velocity is changing in a negative way. It tells you that over here. If the velocity is going down, the acceleration has to be negative to cause that velocity to go down. And sure enough, right there, the acceleration has a negative number. You go a little further on the curve, go right here. It's a little hard to see because it's not enlarged enough, but this slope of the velocity is more negative than this slope. So the velocity is changing more rapidly at that moment. Therefore, the value of acceleration must be more negative at that moment to cause that velocity to change more quickly. I don't know if that helped or not. Other questions? If it's still bothering you, like, seriously, don't just kind of let it sit and just move on, and then with time we keep talking about it, it will get better. Or just come talk to me like lunch before school after, we'll talk more. Anybody else? Okay. Other questions about this? Next one. Do that one, go, 4. Talk to me about anything. Do number 4. It's okay. That's great. That's what that part is. Here you go. 2 Woods is here. You have a good analysis, that's why you get hung up on it. No, I'm serious. Like, it's not a joke.
What's your max?
No, you do. That's why you see it the way that we get it setting up. It's a key to the class. Okay, the students, you just go, I don't really understand that. Oh, well. Yeah, the test will like come back.
You
So
do
just-
5 reps at 1 week.
So you're right. From this time to this time, every value of the acceleration is positive.
I don't know if it's true.
I guess I just got that. We should go get math, the acceleration.
We did flat bench maxes yesterday, but I forgot about it, so I did chest the day before.
But I
So
just
I'm in there
thought.
super sore, like ready to hit legs. He's like, alright, flat bench maxes. I'm like,
Oh, gotcha, that's a valid thought. It's just not mathematically what's in it for you. So that means your logic is good. You just have to know it was serious. Your logic is right. You're thinking the logical way. You just have to adjust the logic.
You're right, you're right.
Okay, so I agree, it's a little bit weird, but it's the way they define it. If I have y coordinates, like this value of velocity compared to this one, am I getting more positive or
No,
negative?
no, it's not. You're wrong.
Because those numbers are going down, we sit here and very simple.
Look, look, look,
Oh, yeah,
look.
it's confusing because when the speed's increasing.
No.
The speed is digits. So the speed's going, like velocity is going -10, -20, -30. So velocity is going. But speed is going 10 to 30. Yeah, that's weird. So in this example, I'm talking about speed, so don't worry about it, it's actually simple. When the values go down, and then it's hard. Speed is not a part of it. Don't worry about it.
But I don't get it.
Straight. If velocity is going down, the acceleration must be
I got him.
All right.
Oh, wait, what did I do? Oh, I'm stupid.
No.
That's right. Alright, anyways.
Okay, the velocity graph is decreasing from point 202. The velocity graph is decreasing all the way to 3.298. They're asking us to, we're making a correspondence again between velocity and acceleration. And Danika's chart has the reminder. When the velocity graph is decreasing, the acceleration values will all have to be negative during that same time period. And you see it right here. Every one of the y coordinates on the red graph, every one of those y coordinates has a negative value. As soon as those y coordinates switch to positive, the velocity graph has to switch and start going up. Questions about that? Awesome. So this is negative for the same time period. The velocity function has a blank or blank at this time, so we're looking right here. That would be a relative max, relative or local max. And therefore the velocity function also has a critical point there. Because the acceleration has a value of 0 at that point. Questions? Acceleration, the number that you see for acceleration, that number represents the tangent slope of the velocity. Very nice. Peaceful. Anybody else? Okay, next one. I'll let you do that at home, that's easy. Last definition of the day. Okay, the last definition is the word inflection point. Oh yeah, please ask me, please.
Number
5.
What is it like saying the acceleration graph is doing from 0 seconds on?
So the way I figure that out, Aspen, 2 points for asking, is again, I have to see what the worksheet is asking me to match up. What am I trying to see corresponds? So I don't know how to fill in the blanks yet.
Yeah.
I know we're talking about acceleration. We're going to start over here at time 0. And we're comparing that to the velocity graph's concavity. Now I can use Danika's chart to put the two together. So when the velocity, if I'm looking at the concavity of the velocity, that will correspond to the increase or decrease of the acceleration. So, acceleration graph from time 0 to some time, oh, I got it now, follow acceleration. Right here, Aspen, is acceleration increasing or decreasing?
Decreasing.
How about here?
Still decreasing.
Still decreasing.
And it decreases to 1.7.
Perfect. So that's what they want you looking at. So the acceleration graph is decreasing from time 0 to 1.75, meaning that in that same time span, the velocity graph must be concave down.
Is it because the acceleration's decreasing?
The definition of concave down is if velocity is concave down, that means the tangent slopes of the velocity are decreasing. But the tangent slopes of velocity are the y-coordinates of acceleration. So if velocity is concave down, the y-coordinates of acceleration have to go down because they're the same thing.
So if acceleration was increasing, it would be concave up.
Then velocity would be concave up, just like you see here.
Decreasing or down.
Yep, just like you see here.
All right.
2 more. There you go. Same time here. Okay, the last definition is the word inflection point. It's on your salmon sheet. Inflection point simply indicates where a function changes concavity. But once again, the definition gives you multiple ways to identify that. So look here. The definition says any function. So as an example, think of the function as being position. One warning. In this chart, I have position above f itself, and I have velocity above f prime. That doesn't mean you should always think of velocity as being f prime. I've seen AP problems where they will call velocity the f function. The chart goes on forever. Like you can just keep drawing it. Column after column after column, the pattern just repeats forever. So you can put these column headings anywhere you want. They just have to always be in the same order. So it always has to be position, velocity, acceleration. So I could have easily put the position here in this column, thinking of position as being f double prime. It doesn't matter. That would make velocity f triple prime. Okay? Just be aware of that so you're not fooled on some future question. So anyway, inflection point means this. If we're talking about position, so any function would be position. That function has an inflection point when that same function changes concavity. So that would be here on Danika's chart. We'd be looking at the position graph doing this, changing concavity. But you can identify position changing concavity by identifying a completely different type of change on velocity. So the velocity graph is going to change this way. That's not an inflection point on velocity. That's an indication that position has an inflection point. So for example, raise your hand if you can tell me, where does the velocity graph change from increase to decrease or vice versa? Hands up. Where does the velocity graph change from increase to decrease or vice versa? There we go. Let's go, Blake. So right here, raise your hand if you would say that the velocity graph is changing from increase to decrease or vice versa. 2 points, 3 for Blake. That's a spot where velocity is going down and then back up. That's a relative min on velocity. But that relative min on velocity is also telling me that the position graph is going to change concavity at that spot, and it does. Here's position. Position is concave down, still down, still down, still down, still down, concave down, concave down, concave down, stop. That's the exact moment when the position graph switches and becomes concave up. And because the position graph is concave up forevermore, you can be guaranteed that the velocity graph will increase forevermore. The whole point of this entire packet is like getting you good at seeing how the two things correspond. Questions? Please.
Why is the position graph considered to be concave up right there? It's still going down.
It's very difficult, too, for Lucas to visually identify what's really happening in here, because that portion of the graph looks linear. It looks like a straight line. If you do the computations, you'll find that the slope of the position is as follows. The slope is negative. Now the slope is more negative, more. Right here is where the slope is most negative. After that, it actually starts to become less negative, but you can't really see it. That's why this is so helpful right here, because would you agree, Lucas, that pretty easy to see that the velocity is switching from down to up at that time? Right, so that's what you look at. That's your indicator that the concavity on position is actually changing. Well done. Points. Anybody else? Cool. That's inflection point. So it says here, the acceleration graph, and let's see what they want us to find a correspondence here. Acceleration compared to the velocity's concavity. So we're down here now. So the acceleration graph is something to times 7. Oh, I got it. It's increasing right here. So here's the velocity graph going up. Sorry, acceleration graph going up. So acceleration graph is increasing from time 1.750. Come on. Yeah, to 7. Therefore, velocity must be concave up for that same time frame. Therefore, the velocity graph, you can see it. Here's velocity being concave down. And right there is the spot where velocity switches from being concave down to being concave up.
And that point is called the inflection.
And just add one extra thing to that. It is the inflection point of the velocity.
Yeah.
Yeah, perfect. 2 more. Everybody listen to what Aspen just said. Really important you get the habit of never saying relative min alone. You have to say relative min of position or relative min of velocity, or like
So it would be the relative min of acceleration, but the inflection point of velocity.
3 more. Relative min of acceleration right here. Also a critical point of acceleration, but it is the inflection point of the velocity. And yeah, the whole packet is all about that idea, like properly assigning which to which and keeping track of 3 things at once. Please, Izzy.
So pretty much with any graph with concaving up and down, you can find the inflection point by finding the derivative. If you can find the minimum or maximum of that derivative.
That is correct, the relative minimum or maximum. That's what the Danika's chart is telling you. That the concavity of position will change, meaning position will have an inflection point at exactly the same time when the derivative of position is changing from increase to decrease, or vice versa, therefore having a relative what's called extrema. So, 2 more. Anybody else? Okay, you have 14 minutes. I want you to work as much as you can. I'm going to walk. You stop me, talk with me about anything that doesn't make sense. I'll keep reminding you, getting the homework done is not accomplishing anything. Like, you've got to make sense of the homework, or it's a waste of time. So